and there's a gazillion unknowns in it. I'm just going to do a nonlinear least squares fit, and I'll get a set of weights. That's the best I can do. Yeah, Mike.
Anyway, if you look at the magnitude of the weights, you're going to figure out which variables are driving.
I think, there's a temptation to do that, but I think you sort of shouldn't do it. And the reason is you've got all of these things interacting, and you want to go in and look at one thing, it could be really misleading. So I don't think people actually try to do that. Okay, so let's kind of take a...
Very big weight on a very small term.
Yeah.
So there's not, this will just give you the right answer, but not really explain why.
Yeah, keep in mind, this is just a fitting a big fancy function through some data. And it doesn't necessarily tell you why these inputs give you the output. You just know it does. So for these statistical methods, it's kind of like principal component analysis. You find out there's some weird variable here that explains most of the variance, and this one explains the next 10%. But you're really not supposed to look at those individual principal components and try to make much physical sense out of them. Okay, so here's a sort of real-world example from this book chapter here. Wayne Slade, a manual student, was in on this deal. So here's what they did. They had 1,100 data sets of corresponding RRS spectra and chlorophyll values. So they pull these out of these NASA databases. They constructed a neural network that had 5 inputs, which was RRS at 5 wavelengths, and we'll see it in a second here what it looks like. They had 2 hidden layers with 6 neurons each, and they had 1 output, which was the chlorophyll. So now here's what you do. They partitioned their 1,100 data sets. They took half of them for training, a fourth of them for what's called validation, and a fourth of them for doing the final testing of how well the neural network works. Okay, and then they compared their predictions with the corresponding chlorophylls from the CWIF's band ratio algorithm. Okay, so here's what their neural network looked like. They have RRS at 5 wavelengths. They had 2 hidden layers. These are the hidden layers, are the guys that take the inputs times the weights, sum them up, compare them with the threshold, and decide what to make an output. Now, why did they pick 2 layers of 6 instead of 1 layer of 12 or 3 by 4 or 4 by 3? That's once again kind of the black art of this business, and I don't think there's any real rules of thumb about how to design an optimum neural network. I might be wrong, maybe they do now, but they didn't long ago. But what you want to have is enough opportunity for a given wavelength. It's going to go into each one of these processors, and each one of these is going to send a signal downstream to each of its neighbors. So here we really have 5 times 6 is 30 weights to determine. Here there's 6 times 6 is 36 weights to determine. And then here's 6 outputs. So there's 6 more weights, and then we finally get an output. So that's their neural network. And then, yeah.
Go back. So when there's, what is N1?
Oh, N1 is simply node 1 of the first.
Yeah, I get that. But what does it look like?
Oh, so N1.
An equation? Is it
Yeah. So that's doing this work here. So in this case, the N1 node is going to say sum of RRS at lambda I, so these 5 inputs, times the corresponding weights here. So I'm going to call them like W of I. So there's the 410 wavelength times the weight for 410. There's the 443 input times the weight for the 443. So it's going to sum those guys up from I equals 1 to 5 over all the wavelengths. I don't know if there was a bias or not. Maybe there was. I probably wasn't. And then they're going to compare that with the threshold and, see is it greater or less. And maybe they say in their paper, like what they used here, I don't remember that they did.
So that's the question.
Yeah. Yeah, I'd have to go back and look at the paper again. Yeah. But anyway, this is then node 1 here. And actually, let's see, this is from, the weight from I. Yeah, okay, so I think, so that's what is labeled node 1. And then node 2 is summing up the inputs times, I should probably call this like maybe weight between, lambda I should call this like RRS is like lambda and the node number n or something. So for the first wavelength in the first node, there's a weight. The second wavelength and then node 2 is going to have a separate weight. Okay, but anyway, that's...
That one and one, and then that contributes to a whole other
Yeah.
M1, so you have multiple weights on the spectrum.
Yeah,
multiple-
right.
so
And see,
counting on them.
you could add another box down here that was sea surface temperature. And maybe and that's going to connect to each of these things. And it might decide that the sea surface temperature just doesn't matter. Or it may be it's going to have a bunch of weights that, in essence, what you might be saying is sea surface temperature plus RRS at 490 and 510 do a better job than just the wavelengths. But you don't really care about that. You just give it whatever inputs you have. If they're relevant, they will determine their weights. And if it's not relevant, those weights will just stay really small and won't matter.
But if you want to know, you would run it with temperature and without temperature.
Yeah, and then you could
Exact same weight.
play those games.
Better job.
Yeah. Okay, so here's the catch. You have this neural network here. You've got your training set, which was 600 values, whatever it was. If you just keep cycling through the training set over and over and over again, you'll keep getting better and better results. But somewhere along the way, so here it says mean square error of the neural network between the output and the predicted output and the correct output. As you cycle through the training set, and these are called training cycles or epochs, as you just keep going through the training set, you'll keep getting better and better results. But somewhere along the way, you're really not fitting physics anymore. You're fitting random noise or biases or whatever in your data set. So you don't want to do that. You want to capture the physics of the biology, but not the random noise in your data. So that's where this validation set comes through. So you do your training, and at each step, you say, okay, I've got a new set of weights, here's my output, or here's my error. Then you go apply the neural network to the validation set. And its error keeps going down. And remember, it's an independent set of values. You go to the next. Finally, somewhere along the way, the training data set will keep getting you smaller errors, and the validation set will start giving you worse errors. And then you know that this improvement comes from fitting the noise, not from fitting the physics. So you use the validation set, and when this starts happening, you back up and say, these are my optimum weights. And so you stop, you take those weights, you've now trained the neural network. Then you go and you apply the neural network to your, what did I call it, not validation set, the testing data. So we've used 600 for training, a fourth for validation, and now we're going to use the other fourth of our values to test how well our neural network performs. Okay, so here's the test. In the training set, when they applied to that, the CWIFS algorithm, for example, fitting values, gave an R squared of 0.65. The neural network was 0.92. But the real important thing is we now apply it to independent data and see how well we did. Well, with the testing data, the independent data was not used for training, was not used for validation. CWIF's R squared is 0.55. The neural network's about 0.87. The RMS error in the chlorophyll went from about 0.5 down to 0.2 milligrams per cubic meter. That's a nice improvement. So here's the plot. Here's the real chlorophyll value measured in the field. Here's the value estimated by the CWIF's OC4 algorithm. There's the fit of points that give you this R squared and this RMS value. With the neural network, here's the right answer. Here's the neural network values, and you can see it's a better retrieval, period. Okay, so here's an example then of that applied to the Gulf of Maine, CWIF's algorithm versus their neural network. So here's the chlorophyll in the Gulf of Maine generated by applying the neural network to the CWIF's RRSs. And so, okay, you get something that's, I suppose, believable if you know how the Gulf of Maine works. So here we are up here. This is a cloud. This is, Canada here, Gulf of Bay of Fundy and all of that. Well, here's now the difference in the neural network and the OC4 chlorophyll values. And so you see for a lot of the sort of open water areas, it's kind of this light kind of yellowish blue thing. That's no error. So it's doing fine here. But you look along the coast, all this case 2 water here, the chlorophyll, this is log of chlorophyll, the log is minus 1.5. That's a big error because remember we got to take 10 to this. So there's big differences in the retrieved chlorophyll in these coastal areas, and then here's a patch or two out here in the ocean where there's the chlorophyll, in this case neural network is bigger chlorophyll than CWIF's, and here the neural network is giving you significantly less chlorophyll. Well, of course, what you're seeing here is this CWIF's algorithm is for case 1 water. So it's working okay out here. It breaks down in these coastal areas where you've got all this CDOM and stuff coming down the Damariscotta River. But the neural network doesn't know anything about case 1 or case 2 or minerals or chlorophyll. It doesn't care whether there's minerals in the water. It just says, I've got a bunch of weights. You feed in I knew the right answer. I have weights that will reproduce that. So it's very nice in the areas where you might suspect the differences would be greater, the coastal areas, that's indeed where they were the greatest. Okay, so it's a nice example of using a neural network. Colin. Yeah.
Right, so it's beautiful because it's actually using the full spectrum, whereas it was just using the banded shield.
Yeah. And so now I can't take the neural network and back up and say, okay, I'm looking at the weight that goes from here to here and from here to here and here and say, oh, gee, 410 was really important in coastal waters or whatever. I mean, that's just not the way you're allowed to look at this. All you know is I can take these wavelengths and get better output than I can do by looking at the ratio of this one to this one, bottom line. Okay.
So did they do that before or after atmospheric correction?
Well, this is assuming the atmospheric correction has been done. I'm pretty sure. They're taking the CWIF's RRS after atmospheric correction.
Constant Herzog has an interesting paper. Vicarious calibration is usually called SVC, system vicarious calibration. Every time, because it includes the atmospheric correction errors, and so every time you change your atmospheric correction, you should also redo the vicarious calibration in general. And so he has a paper about how you deal with a vicarious calibration with a neural net with these non-traditional systems.
Yeah.
to go to ocean bottoms. So it's part of, the atmosphere is part of our,
Probably the calibration student.
well,
Yeah. Okay.
principle, again, you don't have to go through these two steps.
Okay. So take-home messages here are that these statistical methods, they're highly successful. They're widely used. On the other hand, intellectually, there's kind of, and especially with band ratio algorithms, not anything new to do. You just have new and better data sets, and you kind of get better results. But also keep in mind that you're training you either have a model for the band ratio algorithm, or you've trained a neural network, and all of that has means you've tuned your model for a specific place and time or some particular data set. So you're not going to take a band ratio that was tuned for the North Atlantic and use it in the Antarctic. You're not going to take a neural network that's based on North Atlantic data and use it in the Antarctic. Same as any other kind of model or statistical model. And the statistical nature of the algorithm sort of obscures the underlying biology and physics. You just have a black box that gives you the answer. Yeah.
So, I totally understand why they would only work regionally, but like, how does the cat algorithm work then? Because Google is probably, like, their cats are all different shapes and sizes, right? Just like oceans.
That's what's so astounding to me. Now, if you look at the cat neural network, it's probably got like, I have no idea. The inputs are probably like shades of color or something, I don't know, pixel by pixel. And of course, they mentioned there they have 16,000 computer processors doing this analysis. So the neural network probably has millions of nodes and weights in it. And I don't know, talk to Google and find out. They're not going to tell you, but
Data set would be global too for the cats, for instance,
Is
right?
it just the computational limitation? Is that why?
They said in that little blurb you showed, it said that the training set was 20,000 images, and then it started to be able to figure it out.
yeah.
So if we had 20,000 images or 20,000 data sets in every part of the globe, we could probably
Like
train
a
it pretty
global
well.
ocean color satellites and stuff.
Yeah.
Google uses a specific term, deep learning, which is actually a very, very specific type of neural network implementation. It does, they have 20, 30, 40 layers, and then they adjust those back individually, each one, and it's a feedback thing. You end up getting bits and pieces where things start telling you, this is the ear of a cat, and you start layering all these things together, and that's kind of, it's very computational heavy.
Yeah, it helps to have like billions of dollars to spend on this stuff. Yeah.
So as long as your training data set has a feature that is universal to, the full population of samples, the neural network will work.
Yeah. I mean, you're assuming your training data set describes it is similar to the area where you're going to apply the neural network.
Another take-home message will be anytime that you have a problem that is bigger than 2 dimensions and you don't know the mathematical relation between those variables, then perhaps go for a neural network.
Well, you don't have to. I mean, I could have some big function that says I've got 5 RRS at 5 different wavelengths, and I have some big function here. You plug in all those numbers and you get out chlorophyll. And that could be, it would actually be what's called a semi-analytic model, perhaps, that I just don't know what that function is. But I could sit down and maybe think, RRS at 412, well, that's kind of important for CDOM, but 555 isn't, and I can maybe cook up this function without having to use a neural network or a band ratio. But I don't know how to do that. I don't know enough biology to write that equation down. Yeah.
I wanted to get a sensitivity analysis to figure out which variables are important. It would be unreasonable to just construct a neural network with every combination of your 5 wavelengths.
Yeah, you could play games like that. You could, plus or minus values on your input RRSs and see how that changed things and so on. I don't know what all the latest that people do on that is, because there's a huge community of people like computer scientists and mathematicians that sit around and think about error propagation and optimum design of neural networks and all of this, and I don't know what those guys are up to.
But isn't that true also for statistical methods versus predictive? So it's not exclusive for neural networks. It's also
No,
for anything.
it's exactly, I mean, the band algorithm is, gives you an answer, it doesn't tell you why.
But the
It gives you an answer,
statistical
but this one
one,
gives you a much better answer than a band.
the statistical one are limited in the relationship with you. I mean, many are functions, These allow you to explore functions you didn't consider in a sense. You have a much wider possibilities of interaction than the mathematical relationship we use in statistical models.
It sounds like if you're using statistical, you might be wrong, but you know why. If you're using neural network, you might be wrong, but you never know why. Because you don't know the probabilities.
And it's easier to analyze the statistical functionality. But we don't know the 10 to the log 10, OC4, we don't know. There's no mechanistic for us. It's easy to draw it and you look at what it does to reflect it. But we don't know that it gives any.
Yeah.
I was wondering how sensitive the neural network is to the initial weights you give to the neural network. Does it get stuck like kind of in different...
Once again, in principle, it doesn't matter what initial guesses you use, you will eventually get a set of weights that gives the right answer.
So it always converges to the same set
Well,
of weights?
once again, no, I think you can converge to a different set of weights and still get the right answer. And that would depend on the initial guesses. And I don't know if convergence is always guaranteed or not. You maybe, if you make such a bad set of initial guesses, the thing will just never get there. I don't know if there's, I'm sure the mathematicians have all the theorems on that, but
Also, you were training a data set that contained contradictory information, couldn't it? So then it would obviously have difficulty converging on that.
yeah. So it's a tool, it's not the final answer by any means. Okay. And then, these band ratio algorithms are operationally useful. They're still in use for the very latest satellites. But intellectually, they've kind of been milked for all they're worth. You can get, a fancier band ratio algorithms and a fancier curve and more data, but intellectually, it's all just kind of the same thing. And the neural networks now seem to be just kind of taking over the world. And when you have your little Alexa thing and you say, Alexa, tell me where the nearest pizza place is in Damariscotta, there's not somebody on the other end. There's a neural network that's recognizing your voice, picking out words like pizza, going to some map, and all of this. So, yeah, Catherine. Okay. Which you get faster from Colin than you would this thing, but yeah, a real neural network. Yeah.
So it seems like the reading that I've done in the band ratio literature, the constraints on like where they work and where they don't are pretty well understood. Is that correct? But the question that raises for me is that how much has that been adapted by the management community? Like if we do know where they work and where they don't and how well they work, has that kind of been translated out to industry yet, or are people?
I would not agree that it's not
Okay, so I've rafted the Grand Canyon twice as leading Sierra Club trips, and one of the trips I found what was like the most beautiful rock I've ever seen. It's about like this big, maybe about that high and that wide. And what was so cool about it, it's below a formation called the Muav limestone, which is early to mid-Cambrian, about 500 million years old. And it's got these red bands in it, and then there's gray bands of limestone, and there's another red band. And if you look at the isotope ratios of things like carbon to nitrogen to phosphorus or sulfur or whatever, they're different in the red bands than they are out here. And the reason is that living organisms have little bit different ratios of some of these things, or maybe they're looking at oxygen 16 versus oxygen 18 or whatever that is that they do. And so they conclude that these reddish bands are actually fossilized algal mats, because this limestone was laid down in a shallow sea, probably a few meters deep, and there's these layers of scum on the bottom that then eventually became it can build up these thick algal mats. Storm comes along, puts some more sediment on it, and they finally get fossilized. And you see a lot of rocks with this kind of structure, that those are fossilized algal mats from a period when the dominant form of life on Earth was pretty much algae. It wasn't a lot going on. But anyway, it was this phenomenally beautiful rock. It was just polished by the river. This was right down by the edge of the river, just polished to where it was shiny, and it was beautiful colors. And I'd love to have that on my desk at home, but A, it's illegal to take rocks out of national parks, and B, it was big enough that I couldn't dig it out. So anyway, and I have to set a good standard as a Sierra Club leader that we don't rip stuff off. So anyway, if you haven't already rafted the Grand Canyon, I suggest you do so immediately. Here's what you'll experience. So here we are. These are the kind of rafts we use. And there's a place called Lava Falls, which is the biggest runnable rapid in North America. And so here's a sequence of shots. I'm standing on the shore getting one of the rafts going through Lava Falls. There are standing waves. They're so big that the rafts actually bury and go under the waves, and they break over you. So they're completely have gone underwater and are coming back out the other side and popping to the surface again, and then heading on downstream. And this is Dead Man's Rock here. And so you have to go through these falls. You have to make a sharp left turn, drop around to the backside of the rock. Down about here, about 4 or 5 meters underwater, the water has worn a hole through the rock that's about this big around, and it's kind of a tunnel that goes through the rocks. So when you go around the backside and you look upstream, you can actually see light coming through this tunnel. And I know there's at least one person that's fallen out of a raft and been sucked through the tunnel underwater with nothing but minor scrapes. So anyway, that's the Grand Canyon, and you definitely have to do it. We've had a lot of discussion in this class, which is good. So we've now used up half of Colin's time. And so it's about 10 till now, so 5 after or something. Whatever you want, Colin.
I want to just make one little comment about your rock. I think it's a stromatolite, which is cyanobacterial, which relates right back to what that you saw at the beginning.
Well,
So I was trying to make the connection between what
if you guys ever go to the Grand Canyon with me, I'll take you to a place. You go down Nankoweap Creek, and you go to a little saddle to the next creek over. You hike up that saddle and you get on the top, and there are these fossilized molar form stromatolites that are like this big, and some of them are broken in two and kind of fallen over, and you can just see every layer of the stromatolite in there. I don't think that this is a stromatolite. This is Muav limestone, but yeah, you can find some stromatolite. Okay, anyway, I'll believe you then. Yeah, there was a place where there were just everywhere on the ground these big, huge fossil stromatolites, where once upon a time, they were like the dominant form of life on Earth. It was just phenomenal. And of course, I'm going around, I'm totally like just berserk. Look, stromatolites, stromatolites. And everybody else is like, well, I just see a rock, you know. So you really need to take a geology class and then raft the Grand Canyon, because it's, yeah. It's one of the few places on Earth there in Shark Bay, Australia, that still have these big stromatolites that are amazing things, still alive, but not very many places. Okay.